Hi, my name is Robert Kennedy. Thank you for taking the time out of your day to check out my poster, which covers my work from the summer 2020 internship I just completed. Um, let's begin. My poster is entitled GPU Accelerated GNN Bundle. As I said before, my name is Robert Kennedy. I'm a PhD candidate at Florida Atlantic University, which is in South Florida. My advisor is Dr. Kosh Kaftar, and my mentor, LexisNexis mentor this year, was Tim Humphrey. I'd also like to give a special thanks to Roger Dev, who is the creator of the GNN Bundle. He was definitely helpful along the way. My project goals were to add GPU acceleration to the existing GNN bundle to provide HPCC Systems a distributed GPU accelerated neural network training capability. Previously, GNN was limited to just using a CPU for the actual computations. This work aimed to expand that bundle by incorporating GPUs. It leverages a single or multiple GPU cards across a cluster. These GPUs can be, or GPU can be on a single machine, or they can be across multiple machines, or even multiple GPUs per machine in a system made up of multiple machines with multiple GPUs. Another project goal was to run experiments that evaluate the performance benefits of using a GPU over a CPU. So the existing GNN bundle created by Roger Dev allows the ECL developer to train artificial neural networks, abstract artificial neural networks, and predict using artificial neural networks on a HPCC systems cluster. It can utilize one or more Thor nodes, ideally more than one. But before this work, it was limited again, like I said, to just a CPU. Deep learning architectures are large neural networks that are characterized by having both a large breadth of neurons and a large depth of layers. These models get very large very quickly, and they also benefit from training on big data, lots of data. So you have a very large network with millions and millions of parameters, some of these, and you train on very, very large data. As a result, the computational requirements can quickly exceed what a traditional CPU can offer, just because it's, a CPU is a very general purpose processor. It can do everything very, very well. Meanwhile, a GPU is much more focused, and it can do a fewer set of computations much, much quicker. So when we add hardware acceleration to this GNN bundle, it's taking advantage of these GPUs and their ability to do certain type of calculations much more efficiently. Luckily, these types of calculations work well with the training process of neural networks. If you've ever done any kind of neural network training on your own own cluster or your own local machine, you'll know if you have available to you a GPU that offloading basically the forward and backward propagation of a neural network onto the GPU, even a small, inexpensive GPU is significantly faster than using a CPU. If you look here in the lower left-hand corner of the poster, you'll see that the difference can be quite drastic. This simple bar graph shows the speed up between a dual CPU, a dual Thor cluster, and a dual GPU, also a dual Thor cluster. It's about 9.2 times faster training on the GPUs than on the CPUs. This speed up, as we'll discuss later, has been demonstrated on rather inexpensive GPUs, older GPUs. They're the NVIDIA K80s. So using a more modern or newer GPU, you would likely see a much larger increase in speed up. And the speed up here is just measured in the total amount of training time, and how many times faster is it on a GPU. To evaluate my work, I ran some performance tests. I ran where I trained 3 different neural network models of varying sizes on 3 different data set sizes on multiple cluster sizes. I had clusters with 2, 4, 8, and 16 nodes. I compare the traditional GNN setup, which is using a CPU-enabled Thor versus a GPU-enabled Thor. And I also compare that to the optimal speedup, which would be a linear speedup. So for instance, if you have twice as many nodes, it should be a linear speedup would be twice as fast. However, that's going to be unobtainable because of communication costs. So it's a theoretical maximum. As you can see here in the performance chart, the red line is a CPU time, green is the GPU-enabled GNN training time, and then the blue line at the bottom is the maximum theoretical speedup, which is the linear speedup. This is plotting training time of a particular neural network compared to the number of Thor nodes used to train that neural network. So as you can see, as you increase the Thor nodes from 2 to 4 to 8 to 16, as you'd expect, the training time does reduce, but you can clearly see the difference between the red and green line is the difference between a GPU and a CPU, all other things being equal. It's worth noting that this graph here, the axis is not linear, so the differences are even greater than it visually looks like. But as you can see here, a 2 Thor node cluster as a CPU takes around 3,600 seconds to train a particular neural network on a particular data set, whereas the GPU-enabled, dual GPU-enabled system takes about a little over 450 seconds. You can see the training time drastically reduces as you increase the number of nodes. The training time reduction when using a GPU over a CPU is important, but perhaps more importantly is looking at the efficiency of adding a GPU into the mix. If you look at the graph under efficiency, you can see that generally the efficiency actually increases as both the neural network model size and the dataset size increase. Efficiency here is measured as a speed up factor from going from a GPU to a CPU, or CPU to GPU. The x-axis on this graph is the neural network model size. So 34K represents a model with 34,000 trainable parameters. 6 million and 69 million represent models with 6 million and 69 million trainable parameters. Each one of the colors represents either the red columns are a data set size of 5 megabytes, overall training data set size. The green is a 500 megabyte training data set, and the blue is a 5 gigabyte training data set, the largest of which has about 6 million instances, and this happens to be an image data set. So as you can see here on the left-hand side, for all 3 data set sizes, on the smallest model, the 34,000, you can see that, yes, the GPUs are faster overall than a CPU, but by not very much. In this case, 1.5, 1.4, 1.3 times faster using a GPU over a CPU. Another point, this is an aggregate of all of the experiments. So this is just the average GPU speedup across all cluster sizes. So for instance, the 1.5 times speedup is the average across the speedup of measured at 2, 4, 8, and 16 node CPU and GPU cluster sizes. But as you can see here, once the neural network model gets sufficiently large, the speedup drastically increases. across the board, from the smallest all the way up to the largest data set size. Um, moving further to the right, you can see the model becomes very large and the data set becomes very large. The efficiency increases the most. So the larger the data set size and the larger the neural network model size, the greater benefit you will have when using a GPU. And as I said earlier, traditionally deep learning models are both very large and benefit from training on very large data sets. So as you can clearly see here, the need to have a GPU accelerated GNN bundle is quite real. So how does this all work? I designed the work so that the ECL developer that's already using GNN won't have to make any changes to their GNN workflow to get uh, to take advantage of the GPUs. All you really need is, of course, the latest bundle. At this point, it's probably going to be an experimental branch, and you'll obviously need computers with capable GPUs available to use. So I'd like to thank you for watching my presentation. I really look forward to potentially answering any questions you may have about this work. Please feel free to reach out to me at any time, really, but before the end of the poster competition, before community day, or even after, if you want to use this. Of course, feel free to reach out to me. My email is on the poster, and I'd like to thank you again.